gas. It's all around you. It's in space, it's on Mars, it's designed in your blood and in your soda. It's there all the time and you can feel it. Okay, good news and bad news about gases. First, the good news is that when gases are behaving themselves, it's extremely easy to describe their behavior theoretically, experimentally, and mathematically. The bad news is that they almost never behave themselves. The mathematical description of behavior of the gas was a link between pressure and volume. If we somehow expand the volume of the balloon, the pressure inside comes up. If we somehow expand the balloon, the pressure inside comes down, and it might have a little break by pushing it. The relationship here is a simple one. When you multiply pressure and volume together, you get a constant. It's called Boyle's law. But where is that constant coming from? And why is it different for different amounts of gas and different temperatures? Well, it took more than 100 years before we'd figure out the answers to those questions with the help of a Frenchman, Jacques Charles, an old Avogadro friend. Charles discovered that volume divided by temperature equals a constant as long as the pressure remains the same. And then Avogadro discovered that volume divided by amount of moles equals a constant. Here's the crazy cool thing. All the scientists were dealing with different forms of the same equation, an equation that we must never forget and it must be stuck in your head until you die. Pressure multiplied by volume equals constant number of moles, number temperature. Often written as PV equals nRT. The ideal gas law which works for all gases as long as they behave themselves. And here's a part which shows that all the scientists were dealing with different forms of the same relationship. They were just clamping various variables together. All the chemists we just mentioned, Boyle, Charles, and Avogadro figured out the contribution of the ideal gas law experimentally. But more interesting is that it can be understood theoretically. First, we had to understand what these variables actually mean. In that same way, the atoms and the molecules that make up gases are bouncing against things, applying pressure to them. And we all know that 1 atmosphere equals 101,325 pascals, which almost equals 100 kilopascals. Volume is the amount of space particles that have to exist inside of. So yeah, that makes sense. When the volume goes down, the pressure goes up, because there are more particles in the space. And simply M, the amount of gas, the number of molecules in that system. And then R, called the universal gas constant, which equals 8.3145 liter kilopascal per Kelvin mole. T, which is experienced by you and me as hot or cold, it literally depends on how fast or slow the molecules are moving. It's the absolute temperature of the gas. No? It's a pretty cool thing that if you know 3 things about gases, you'll figure out the 4th. But remember, not all gases behave themselves ideally. Ciao, ciao!